Good afternoon. Welcome to the featured faculty lecture series. I'm Don Mueller, Chair of the Department of Engineering. Featured faculty are identified each year as a way to honor professors whose outstanding research has contributed to the sciences, the arts, humanities, business, and society. The 2011 featured faculty are engaged in the creative process of research every day at IPFW, in laboratories, in classrooms, in the community, and around the world. The featured faculty lecture series is meant to showcase these award-winning faculty and their groundbreaking research. It is my pleasure to introduce today Dr. Hosni Abu-Mulaweh, Professor of Mechanical Engineering. Dr. Abu-Mulaweh graduated from the University of Missouri-Rolla in 1992 with a PhD in Mechanical Engineering. He joined IPFW in 1997. He quickly rose through the ranks and was promoted to professor in 2004. Dr. Abu-Mulaweh's expertise is in the area of heat transfer, with a specialty in convective heat transfer and energy systems. He has published over 90 refereed papers, and his work has been cited in over 150 publications. He has worked on projects that have been sponsored by both industry and grants, and he's worked with many students. In addition to being an outstanding researcher, I also should mention that Dr. Hosni Abu-Mulaweh is an outstanding teacher and provides a very high level of service to our department that's very appreciated. So it's my pleasure to introduce Dr. Abu-Mulaweh.
Thanks, Bob. Thank you for coming. The title of the presentation is Energy Applications for Daily Life. This is a brief outline of my presentation. First, I'll be presenting a brief introduction and some background. Then I'll be presenting 3 energy applications, time permitted. First is extended surfaces. Usually we refer to them as FENS. Second, design and performance of a thermosyphon heat recovery system. Third, development of a benchtop air-to-water heat pump experimental apparatus. First, the question is, what is heat transfer? Heat is defined as thermal energy in transition. What about heat transfer? It is a process by which transfer of thermal energy takes place between parts of a body or between bodies. However, for this process to take place, there must be a temperature difference or temperature gradient. If there is no temperature difference, there is no such process. Also from physics, heat always flows in the direction of decreasing temperature, from high to low. There are 3 modes of heat transfer: conduction, convection, and radiation. The mode of conduction is the heat transfer between parts of a body or between bodies that are in contact, touching each other. For the second mode, which is convective heat transfer, we must have a fluid adjacent to that surface. And if there is no contact and there is no fluid, that will be radiation. The radiation is the heat transfer between bodies that are separated in space. As long as there is temperature difference, there must be heat transfer. This slide summarizes the basic laws that governs those modes. First, conduction is governed by the basic law, Fourier's law. Convection is Newton's law of cooling, and radiation, Stefan-Boltzmann's law. For conduction, Q is the amount of heat transfer. A is the cross-sectional area that heat is being conducted through it. K is a material property, thermal conductivity, and partial T, partial X is the temperature gradient in the direction of the heat being transferred. For the Newton's law of cooling, A is the surface area from which the heat is being lost or gained. T hot and T cold, that is either the fluid or the surface. And H is that the heat transfer coefficient, and that a very important parameter could affect the amount of heat transfer and depends on many parameters. The last one for radiation, Stefan-Boltzmann law, E is the amount of heat emitted from the surface. Epsilon is the emissivity of the surface, and it ranges between 0, nothing is being emitted, to 1, the maximum can be emitted. Sigma is the constant developed by Stefan-Boltzmann, and T is the temperature. Where do we encounter heat transfer? Believe it or not, everywhere. These are very few examples. In mechanical engineering, We have in heat engines, heat exchangers, air conditioners, power plants, and so on. In aerospace engineering, rockets, space vehicles, electrical engineering, motors, generators, electrical equipment, and so on. Believe me, everywhere we face it. Now we'll start with the first energy application, which is the heat transfer from extended surfaces or fins. Fins are usually added to increase the heat transfer from the body. Why is that? Because when we add fins, we increase the surface area from which the heat is being lost or gained, for that matter. The heat lost now from the surface to the adjacent fluid, that's convection, and that's Newton's law of cooling. If we have T hot and T cold, and we have the H doesn't change, the only parameter that we can play with is the surface area. If we can increase the surface area, we can increase the heat loss. Now, you wonder why the elephant has very large size ears. I think God knows better, right? The ears of the elephant acts as fins. If H is constant, we can increase the heat loss by increasing the surface area, and that's why we have so large ears. Also, sometimes you see those ears are flipping. Why? Again, I think the elephant is smart enough to know that if those ears are flipping, that will increase the value of H. Why? Because some movement of the air that affects the value of H increases, so both we have large ears and flipping, more heat lost from those ears, cooling the blood. Now we go to man-made. This represents a cooling system for a microprocessor mode. This microprocessor, when it operates, it generates heat. We have to dissipate it, we have to lose it, otherwise it will stop functioning. Again, T hot, T cold are constant, H is constant. The only way we can increase Q is by adding those fins to increase the surface area, so we increase Q. Now we have Pentium 4, the previous one was Pentium 3. That requires more dissipation for the heat because it generates more heat. That's why here, these are the fins, and we are in the fan. Now the fins increase the surface area, the fan increases H. Another example is the household radiator. In this case, we're dissipating heat by two modes, convection and radiation. Convection to the surrounding air, radiation from the radiator itself to the walls, to your body, and so on. This slide represents various extended surfaces. Here we have a square with a constant cross-section area. Here we have variable cross-section area. Here we have circular with constant cross-section area, and so on. These are the cases usually studied academically. And I have to acknowledge that all of these studies I'm presenting were done collaboratively with Dr. Mueller. This is the setup for the experiment, where we have a heated plate. There we have heating element sandwiched between two plates to generate the heat. And this rod represents the fin. We instrumented the fins with several thermocouples at different locations to measure the temperature. And here we can adjust the level of heating by using the variable voltage transformer. And this is the readout for the temperature. We could set up the heating at a certain value, wait for 2-3 hours to reach steady state, then take the readings, and so on. Then we formulate the model to predict what the experiment measurements, to compare with the measurements of the experiment. And this case represent the model consider two modes of the heat transfer, convection and radiation. This sample result, which compares the measurement with the numerical model. We use final difference. As you can see, very good agreement between the model and the measurements. Also, we concluded from our study that the amount of radiation is about 15 to 20% comparing to the total heat transfer. This will be by convection. Second energy application is the design and performance of a thermosyphon heat recovery system. This was supported by a grant from the American Society for Heating, Refrigeration, and Air Conditioning Engineers. The objectives of this study is to recover waste heat from a window air type air conditioner to heat water for residential and commercial use. We're going to do that by constructing a thermosyphon heat recovery system. This slide shows a schematic of the system that we dealt with. This box here represents the air conditioner, and this is the storage tank, and this is the heat exchanger that we built. The air conditioner has three processes or three components. There, the evaporator, where it will remove the heat from the inside of the house to the refrigerant inside the evaporator. Then it goes to the compressor and to the condenser. The condenser will lose the heat to the outside. We are saying instead of losing this heat as waste to the outside, we're going to recover it and heat water with it. So we're going to bypass this condenser and go from the compressor to the heat exchanger and heat the water with it. So in the heat exchanger, water is heated by passing the superheated refrigerant. R22 is the refrigerant, enters the heat exchanger from the top and the water from the bottom. The hotter water flows upward through the connecting pipes into the top of the storage tank as a result of buoyancy. As you can see, we are not using a pump for the water. We're using buoyancy, thermosyphon. When the water is heated, the density gets lower, it goes up, and the cold water will be replaced by colder water than is being heated. As the hot water leaves the heat exchanger to the top of the storage tank, and the cold water will enter instead of it. In this arrangement, as you can see, whenever the refrigerant flows in the coil, water circulates between the heat exchanger and the storage tank. Now, what is the thermosyphon effect? Thermal esterification is formed when the water is heated by the superheated refrigerant passing through the water heater, as I explained earlier. And by separating the water heater from the water storage tank, a thermosyphon circular loop connecting the water heater and the water storage tank can be established. These are the two examples of the water heater or the heat exchanger that we developed and designed. The first one is concentric heat exchanger, basically one tube inside the other. And the other one is cold heat exchanger. We have a coil inside a chamber. In this, we were showing how we retrofit air conditioner to bypass the condenser, and the refrigerant will go through the heat exchanger. This is the final setup where we have the air conditioner, and this is the retrofit pipes. That's the water heater or the heat exchanger, and this is the water storage tank. These are sample results for the concentric heat exchanger. We took measurements at 3 different levels in the storage tank, at the bottom of the tank, the middle of the tank, and the top of the tank, and we recorded the temperature with time. And this is how it shows that as we operate, the temperature increases, and it shows the thermosyphon effect. At the top is hotter, then middle, then the bottom, which is the lowest temperature. Same trend, we see it in the other heat exchanger. The difference between them, in this heat exchanger, it gets hotter, the water gets hotter very, very quickly. The second one, it takes a while to reach the maximum temperature. These are some concluding remarks. We have seen that the thermosyphon recovery system that recovers wasted heat from a window can be designed, developed, and constructed. Results indicate that thermosyphon effect can be used to recover some of the heat rejected from the air conditioning. And this method is very attractive because we don't use a pump to avoid some mechanical problems and noise. The third energy application is the development of a bench-top water heat pump experimental apparatus. Again, it was supported by ASHRAE. The objective of this project is to develop and construct a bench-top to water heat pump experimental apparatus for instructional and demonstration purposes in our classrooms and laboratories. Why not just buy such apparatus? It's very expensive, budget is very limited, and most of the time it only does one single experiment and very bulky. Usually the size, you cannot move it from one class to another. The system requirements and specifications, again, portable, so you can move it from one place to another. Capable to perform multiple experiments, more than one experiment. We have to design it around the vapor combustion cycle, and the reason we cover this in our classes. And we have to instrument it it can operate standalone and with a computer. This is the final product that we have designed and built. This slide shows that the two loops, that of the refrigerant and that of the water, and it shows what are the kind of measurements we take for the temperature, pressure, flow rate, and so on. This simply to show that this box control and give us the readings for the pressure, temperature, flow rate, and so on. And this, if we as a standalone, and if we want to collect the data, we just hook with this to the data acquisition with the computer. Again, if we are using the data acquisition with the computer, this is the panel for that control the temperature, the flow rate, and the pressure. For the temperature, that of the refrigerant, and that's of the water. Same thing with the pressure and the flow rate. The heat pump system can be used for different experiments: open loop, closed loop, closed system, and system cooling. So for different experiments, we can use this system for. This table shows the configuration for each one of those experiments we need to run. Just go to those valves and follow this open, close, and so on. That will guide you to the experiment you want to run. This is sample results for one of those experiments, and this is for a steady state closed loop configuration. And we ran it for 3 times to show the repeatability of the experiment that can be repeated with accuracy. Run 1, run 2, run 3. And basically, there are the measurements for the temperature of the water, temperature of the refrigerant, and the pressure of the refrigerants at different states in the system, as can be shown in this figure here. This is we plotted those 3 runs. Again, as you can see, the temperature of the water increases in the storage tank, and those different colors for the 3 different runs, as you can see, very good repeatability of the system. We developed a thermodynamic and heat transfer model using engineering equation solver. E stands for engineering equation solver. And here we are comparing with one of those runs with the model. How can we predict it? So we compare experimental result with the model prediction. As you can see, not too bad. Another results we are interested in from thermodynamics aspect is those values. First, the chemistry required to run the system is 634 watts. And again, this is being from the measurements. Because when we measure the temperature and the pressure at a certain point, we can get those values. H stands for the enthalpy. So we can get those values and evaluate those quantities. So that's the work of the compressor required, the rate of heat transfer from the condenser. And if we know these two values, we can calculate that of the evaporator, because the work of the compressor plus the evaporator, that of the condenser, need to be dissipated. Coefficient of performance is that Q, the condenser, divided by the compressor, which is 2.4. In conclusion, a pinched top air-to-water heat pump was designed, developed, and constructed for the demonstration purposes. The system is fully instrumented. The system fully controls and monitors the fluid properties at key points of the refrigerant and the water loop. The apparatus has an intuitive user interface, reliable, safe for the students to use. The interface is capable of allowing data acquisition by the computer. The unit is also instrumented with autonomous gauges to be able to demonstrate heat transfer principles and thermodynamics processes without needing to hook up for a computer. Thank you very much. Yes.
Kind of like Joseph's question, and of course I'm not an engineer, have no clue, but I just recently read an article that an engineer from EPA, they had taken the technology of, I don't know, is it rocket booster or convection oven, and they have designed a oven that, like, poor people all over the world can cook their food instead of going and gathering a large amount of firewood, and a lot of them are in danger, just with a couple of twigs. This oven is so much like the properties of the heat that does not waste the heat. So with a couple of twigs, they can cook a meal. And but again, in the spirit of Joseph's question, if you can use this technology to design maybe a coolant that the poor people can use, that would be like wonderful also. But can you comment on that? Are you aware of those convection oven? How could they do that? That rather than loss of heat, very cheaply cook a meal with few twigs, whatever. Are you aware of that?
No.
Okay.
Yes.
For this thermosyphon recovery system, how much energy is actually being recovered? I mean, would it make an appreciable difference on my water heating costs, or would it be minimal?
First of all, this is free. So whatever you get is not too bad, you know. The only thing is just the initial cost. And again, I have to go back to the calculations. This was done like 3-4 years ago, so it's not fresh in my mind. Yes.
What about other applications other than just air conditioning? Could it be used like lathes and milling machines create a lot of heat? Could you run coils through the lubricating materials and heat water and do the same thing?
If we can get that fluid that is hot flow through a heat exchanger, yes, it can be done.
It would seem to me that would have some very significant industrial applications where they use automatic screw machines, lathes, and that kind of thing.
Again, if the heat is going through that lubricant fluid, and we can get that lubricant somewhere to go through the heat exchanger, yes. But from the jet itself, I doubt it. Yes.
So often it seems heat energy is something that is wasted. You mentioned recovery over there, and I'm just concerned with when heat is generated as friction, or due to friction, we just tend to want to dissipate it, get it off the internal combustion engine, get it away from here so that the thing doesn't shut down. Where are we as a science in terms of converting that form of energy into another form of energy possibly that can be reused, recycled? Can we convert it into some kind of kinetic energy that assists in the internal combustion engine's chore, or potential energy somehow? Is there any?
We talked to Navistar about the thermoelectric effect. They want to pack thermoelectric material some places, let's say along the exhaust system, and we talked to them a little bit about it. It costs money to put that stuff on there. It's not very efficient. Mm-hmm. The idea was to convert that heat to electricity to run a fan, to run the air conditioning system.
Now, I'm not an engineer, obviously.
You
can tell by our questions.
We're asking questions, but we have no clue.
Yeah. But in part response to the question that you raised, I think the auto manufacturers have done quite some significant amount of work in capturing what you mentioned. For instance, the Prius Toyota vehicle actually generates electricity from the braking system, and that is recycled, used to power the vehicle later on. So yeah, I think some movement.
But heat energy is so easily lost, and oftentimes we just
true.
want to get rid of it, just dissipate it, instead of trying to recover it.
Yes.
I guess I am an engineer, and I have a commercial. sorry. I have a commercial system in my house. It's been in there for several years. It's an open loop system. They're supposed to recover a lot of energy and then dump it into the hot water heater. Because I'm technical, I put probes all the way through my system to keep track of this. I've found that they're dumping, and the reason I ask about that discharge temperature, they were dumping 98-degree water into 120-degree water hot tank. So it was doing absolutely nothing. I've now modified it, so and I'm, to answer your question, I'm now saving 20 to 25% of my electricity bill because of my hot water modification. But I found it, and this was a commercial endeavors that they actually were selling that, and it's a well-known, very large company, very in town, that's doing this. So I think a lot of it is marketing, touting that we're saving energy, and react probes showing that we weren't saving energy. In fact, it was
Cooling your tank.
taking a little bit away, right? Yeah.
Thank you.
Okay, I would like to go back to your interesting example about elephant ears and the heat sink in computer, right? So both of them are convective behavior, right?
Yes.
So you have equation like heat equal to H times A and the difference of temperature.
Yes.
And you explain that if your air is flipping or you have the fan work on that, the heat H will change.
Yes.
Okay.
But
It's not constant.
no, that's what I said here. Forced convection. When there is no movement of the fluid, that's called natural convection or free convection. If we force the fluid over the surface, that's called forced convection. And H for forced convection is higher than H for natural convection. So if we move the fluid, it's like if you have a surface, you want to cool it with just air, still air. It will cool faster if you have a fan to move the air. What you have changed just H.
Does that imply that if you increase the fan speed, the H will increase as well?
Yes, but to a limit. It's not like exponential.
It won't affect the distribution of temperature. So it's related between H and the difference of temperature, right?
H depends on many parameters. It depends on the shape of the body. It depends on the fluid we are using. It depends on the speed of the fluid. Well, because if we have like going for technical, for laminar or turbulent, if we have turbulent flow, H will be higher than laminar and so on. Other questions? Thank you.